Hello, my name is Ben-Yaakov. This presentation is entitled Recent Advances in Circuit Simulation of Power Electronic Systems. The presentation is actually divided into two parts. The first part deals with a review of current simulation packages that are available commercially and a benchmark that shows the differences in performance and the areas of application that is suitable to each one of them. The second part of the presentation is sort of a short report on some of the area of the research that was done at Ben-Gurion University in the area of simulation related to power electronics. Let's start with the question, why do we want to do simulation in power electronics? Well, the first point that we have labeled as education and exploration is whenever we have a, say, topology or a circuit that we would like to examine or understand, or if we have an idea that we want to see if it really works, then simulation is a very good tool to examine this. We don't have to build it. We don't have to do all the actual construction. We can test it virtually and see if the idea holds water. Another reason for doing simulation is the question of dynamic response or stability related to it. We like to see if the system is stable. We like to optimize the loop gain or any other feedback loops, internal feedback loops in the system. And for that, of course, simulation is a very good tool. We don't have to do it on the real system. We don't have to build it, actually. And if we build it, we don't have the danger of actually damaging the circuit if we do some experiments with the still unoptimized feedback control. Another reason for doing simulation is looking at the transient phenomena. For example, how well do we feed the gate of a transistor, rise time, fall time, things of this nature, snubbers. And again, if we have a good model of a transistor or a switching transistor, we can look at these phenomena. Another point is spread of components, values of components that, of course, will give us an envelope of performance. And we would like to look at the worst case, if, say, the inductor is its minimum or capacitance is its minimum. Then, of course, simulation can very quickly give us results of a variation in the component's value. Another reason is looking at nonlinear effects. For example, what is the effect of a reactor or a inductor that is partially saturated or a powder core inductor? And as the current builds up, of course, the inductance goes down, and this will have an effect on, say, ripple and other phenomena, and of course on the feedback loop. So these are also phenomena that we can examine by simulation. And finally, what is very popular today is the question of digital control. And we would like to design controllers. We would like to examine controllers, and simulation could be a very valuable tool to do that. Now, on the other hand, what are the features that we find in simulator which are related to the problems that we would like to solve with simulation? The first one is the question of convergence. Well, as we know, there are many cases in which simulation cannot proceed because there are convergence problems. The simulator stops, and we have to change parameters of sensitivity, accuracy, things of this nature. And this could be very annoying. So the question of convergence is very, very important, but especially when it comes to power electronic systems. Another question is, how well are the physical models describing the elements we are using? How well is a model of a, say, power MOSFET really describing all its features, like rise time, like delays, and things of this nature? Another important feature that we would like to have in a simulator is small signal analysis. This is especially important in the design of a feedback or control, because as of now, most of the control design is based on the frequency domain, and for that we need transfer function, meaning we need the small signal response. Another question is interfaces. In some cases, we would like to be able to examine the results or do some simulation with another package, for example, MATLAB or Simulink. And for this, we would like to have an interface between our simulator and the, say, MATLAB or Simulink that will be convenient for transferring the information back and forth. Another issue is, of course, runtime. How long does it take? Behavioral models are also very important because some of the nonlinear elements can be described by behavioral models, and I'll show that later on. Also, some of the control could be nonlinear, and for that we need behavioral models. So the question is whether we do have behavioral models implemented in the simulator. And then we have question of statistics and optimization. This is for looking at the spread of parameters and also picking up the best set of values to solve a specific problem, for example, for optimizing the loop gain or the phase margin of a system. And finally, again, is the question of discrete domain simulation. This is important for digital control. We would like to be able to implement a digital control algorithm and see how well does it actually control the system. So taking these into account, we can then map on the one side the tasks that we would like to perform with the simulator and the required features. So for exploration, convergence is very important, small signal important, and also to look at various control and nonlinear elements, we would like to have behavioral models. For the dynamic issue, we primarily would like to have the small signal. As I've said, it's very important. Runtime could be crucial. We'll talk about it in a few minutes. And then behavioral model for nonlinear control. As for transient analysis, convergent could be extremely important because transient meaning we are looking at the really edges of the changes, and then of course the question is how well is the simulator capable to cope with very fast transitions is very important. We would like to have exact model of transistor, diodes, and other elements, and these are really the important issue in transient analysis. For nonlinear analysis, we would like to again be able to linearize the system because we would like to look at the small signal response, and again behavioral models to be able to model a nonlinear element or process. And finally, for digital, we have the question of convergence. We'd like to be able to look at the small signal because our design is based on the frequency domain. Interfaces are very important for digital simulators like or discrete simulators like MATLAB, and behavioral model for implementing a nonlinear control. So let's have a look now. What are the simulators that are available on the market? We have one group which is SPICE based, and they are actually based on a core which was developed many years ago, actually 1972 or something like that, at Berkeley University. And then, of course, all the companies that are using these cores have expanded it, added interfaces, and of course made it more, say, user-friendly and other features added to it. In this class, we have the PSPICE. Which is the mostly known, I guess, and very popular. We have ICAP by Intusoft, and we have MICROCAP by Spectrum Company. Now, we have, however, another group of simulators, and they are not based on the SPICE Berkeley core or engine. They have a different algorithm, which is actually different in each one of them. One of them is PSIM Power Simulation by PSIM company. The other one is Simplorer and PLECS. We'll talk about them in a few minutes. Important package for for SPICE-based simulators are libraries of elements, for example, power transistors, diodes, etc. But as it turns out, most of the simulators based on SPICE don't include models of controllers. So a company by the name of AEI actually is now developing models for controllers. I'm talking about PWM controllers. So one can use these controllers and in combination or within the platform of a SPICE-based simulator, and we'll talk about it a little bit later also. So let's start with the most popular simulator, and that is SPICE. Now, PSPICE, or PSPICE. PSPICE was actually developed primarily, or started with MicroSim company. Now it's owned by or sold by Cadence. It's a complete package, not just for power electronics. Of course, it has many layers to it, and it's being used widely for analog electronics, digital electronics, and some other. And of course, it has interfaces for PCB, circuit schematics, and other programs. It is, as I've said, SPICE-based. It has an extensive physical model for just about all the elements. All vendors of transistors, diodes, and active elements supply actually models for SPICE. It has a library for behavioral models. It can run AC analysis after linearization. It has statistical packages. It has an optimization tool that we'll talk about it later on. And it has some PWM models, but as I've said, it is not does not include actually controllers for the PWM. For that you need another vendor, because they are not provided by most manufacturers of ASICs. And then it has also a MATLAB and Simulink interface. Now, looking at a typical window desktop for schematics of PSPICE, here we have actually here, this is a real transistor, real in the sense that it is a model of a physical transistor, IRF, I guess 830. There is a real diode. And then we have some behavioral parts. For example, the error amplifier is implemented by a voltage-dependent source. And the PWM generated is also realized by a waveform, a sawtooth, and a dependent source. Actually, it's emulating a comparator. Now, the terrible things about PSPICE is, of course, that you get, once you start running, in many cases, you get this window saying that there is a convergence problem, and then you have to start playing with the options, and this is the setting of the simulation, the sensitivity, tolerances, etc., to try to overcome the problem, which is a function of the rate of change of the waveform. That is, if you have a voltage which is changing very fast, as you have in power electronics, the problem is severe, because the simulator is actually changing the step size, going back and forth. So therefore, it will eventually hit the point that the step size is too small, and you have either to relax the resolution of the computation or the accuracy, or some other thing to do. Now, as I've already mentioned, this company, AEI, now offers a set of models for actually power electronics. They have PWM controllers. but then they have models of some other interfaces, for example, transistor or MOSFET drivers, regulators, and some other elements. And this, of course, could be extremely useful in a complete simulation. Let's move to the ICAP. This is another SPICE-based simulator. It's less popular, but the thing that one can say about it is that it is more power electronics inclined. It has some features that I'll not go into it, which make it more useful and helpful in simulating power electronic system. Especially, they have many demo circuits, many subroutines that one can actually borrow and use them as a starting point for simulating some converters. Another simulator, which is now different in that it is not based on SPICE at all, is called PSIM, or Power Simulator. It is a time domain simulator, only in the transient analysis. It is different in the sense that it has fixed steps. It disregards the actual transition. That is, it doesn't try to fight the fast changes. It takes actually a point before and after the transition. So therefore, it doesn't have the problem of trying to match the rate of change, the physical rate of change with the actual simulation. Therefore, it is very fast and effective, and only in the time domain. I already mentioned the constant timestamp. It is capable of doing AC analysis, but this will be by actually injecting small signal in the time domain and looking at the ratio between output and input in the time domain. So therefore, it will take a long time. We'll talk about it in a few minutes. And then it has very nice interfaces, has many generic models of passive switches and other elements like motors. But these are, again, for example, for the switch, it's generic. It's not describing a specific MOSFET, but really the action of a switch. And then it has analog behavioral model library. It has Simulink interface and also interface to a program, which is a finite element program that can produce a equivalent circuit of a magnetic element. Now, the downside is that since it is not looking at the transition, then it can result in some error of the simulation because it is missing some of the transients, and therefore spikes, very sharp spikes will not be actually seen. And also, it has a rather simple output graphics, doesn't have a way of doing the signal processing on a sophisticated signal processing on the outputs. Let's have a look at the window that we get. This will be the capture, schematic capture. All the elements, this MOSFET is generic. That's not a specific MOSFET. It's just a switch that is actually controlled by a unit that turns it on and off. But you can, if you use an amplifier, then you can have, design it to have a given bandwidth, of course. Here we are showing a AC analysis, but again, the AC analysis here is done by injecting a small signal in the time domain and looking how it actually produces an output in the time domain at the output terminal, and the ratio, this will be here, the ratio between the output and the input will be the transfer function. Another simulation we have to run forward is the Simplorer. Simplorer is also a generic type simulator that is dealing with generic elements primarily. It is oriented toward systems. It very nicely can simulate system including drivers, motors, and things of this nature. It is part of the Unsoft package and also has an interface to a magnetic finite element unit, so that you can actually take a magnetic, say even a motor, and generate a equivalent circuit that will run then on Simplorer. And let's go quickly about the features. It has a generic model library. It's very flexible. You can describe system and control in many ways. I'll show you an example. It has a analog behavioral model library, which is very useful, as I've mentioned. One of the features which is kind of interesting is you can implement in it or use within the simulator subroutines which are written in C, so that you can describe a system or a process or a control by actually a C program subroutine implemented in it. And also it has MATLAB and MATCAD interfaces. Now, the downside is it's kind of a little bit difficult with the help. It's different from SPICE, and so therefore people who are used to SPICE or PSPICE will have some training time will be required for them to get into the Simplorer. And again, it's rather limited when it comes to physical models of elements. Here is an example. This is a bridge, and control here is by hysteresis. We see here the implementation as a time machine of the hysteresis. It actually logical decisions are being made as to whether the current is lower or higher than the reference levels, and this will activate the switches of the bridge. And the nice thing about it is that you can see on in one window both the schematics and the actually simulation result, which is kind of very friendly when using it. The final or the last one of the packages that I'm going to mention here is PLECS. Now, this is really not a standalone unit. It's actually a plugin for MATLAB. And what it is that we can describe a system within PLECS and then insert it as a block into Simulink and run it as part of a Simulink simulation. So it's not a standalone, but rather add on to MATLAB, and therefore, of course, whatever MATLAB can do, this package will do, except the fact that it's not describing physical, it does not include physical models of, say, transistors. It's only generic models, switches, diodes, virtual elements or general elements. And of course, it doesn't have any other feature other than what you can find in the schematics or capture of Simulink and at the graphics, output graphics. Let's have a look how it looks here. Here is a circuit which is basically described in PLECS. This is a same flyback that I've shown before, and you describe it as a circuit diagram, but then it ends up as a block into Simulink, and then you can do whatever you want or whatever you'd like to do in terms of within the environment of Simulink, excitation, output graphs, etc. We'll now move to a benchmark that we did, and what we're going to do is really to compare, or we did actually compare the same flyback circuit, running it on the simulators which represent the available simulators today. One is the PSPICE. These are the SPICE-based simulator. PSIM, which is again different in the sense it's a different algorithm. Simplorer and PLECS. So let's have a look at some of the results. We have For the PSPICE, this is the flyback. Again, this is a real transistor, real in the sense that we have a physical model for it and a diode. And the other elements are other passive elements or behavioral elements. And for the case of a PSIM, it'll be, of course, a generic MOSFET, a switch. And passive elements are the same, but the amplifier, again, in SPICE could be real amplifier, real in the sense that are commercial amplifiers that have a physical model, but here these are generic amplifier, although they could have a, of course, bandwidth. This is an amplifier. This will be actually a comparator. They'll have, you can implement final bandwidth per the application. Now, if we look at the results for PSIM, they are very, very, well, we have maybe a few minutes, so let me go back and I'll demonstrate actually the operation of PSIM that maybe not all are used to it. So let's run it for a second and see some of the features. So what I'm doing, I've just opened the PSIM software, and this is again the same circuit here, and I'm now running it. Actually, it's running a little bit slower than it would normally run, because we are capturing this presentation, we are capturing the video, so that there is a program running in the background, and therefore it takes more time. Okay, so this will be then the run, and here are the results. And as you can see, the waveforms are very, very clean. It's like a textbook. We don't see any spikes, any transient. Of course, the person trained in power electronics will look at it and say, well, this cannot be from a real system because, you know, there's no spikes, no oscillation, there's nothing there. So the reason why we get these nice waveform is because, as I've said, PSIM is not looking at the transitions at all. And consequently, it's not trying to replicate what is really happening within this transition, and consequently, you are losing this information. And this has many benefits, of course, because then simulation does not suffer from big or major convergence problems. On the other hand, it's kind of masking some of the features of the circuit. If we compare PSPICE to PSIM, this will be here PSPICE, and this is PSIM, of course, and you can see that PSPICE will show all these spikes and transitions that you'd expect, while in the case of PSIM, you don't see them. If we compare put one result top on the other one, on the average, of course, it's very good, but lacking in the PSIM will be all these transitions that, for checking the performance of the circuit and in understanding how it works, it really not important. Not only that, it's good that you don't have to handle these spikes. On the other hand, if you'd like to look at transitions, rise time or effect of snubbers, or performance of snubbers, then maybe you might have a slight problem. You'll have to decrease very much the step size in order to be able to look at the transition itself. Now, when it comes to small signal analysis, actually there are two ways to approach it. One is working with the full circuit, meaning that we run it in the time domain and inject sinusoidal perturbation, and then look at the output and then take the ratio between the output and the input in terms of amplitude and phase. And when you do it in PSPICE, then you have to do it manually. There's no routine to do it. In PSIM, it's automatic. That is, you specify the range of frequencies. You actually specify the amplitude, or how does the amplitude change, and it will automatically run, except that it will, of course, in both cases, it will take a long time because each analysis is in the time domain of the full circuits with the switching and everything in it. Another way, of course, is to use average modeling, and this is an approach that we have been working on at Ben-Gurion University for many years now. And with an average model, you are actually looking only at the low frequency phenomena. You don't look at the high frequency, you don't look at the switching. And in the case of PSPICE, you would then use AC analysis. That is an analysis that will actually doing linearization around the operating point. In case of PSIM, you still have to do injection of transient of the sinusoidal perturbation. The reason is that PSIM does not do, strictly speaking, AC analysis, that is linearizing the circuit, but it's doing it through a consecutive and running again and again transient analysis on different injections of the perturbation. So let's have a look at result of some AC analysis. Now the blue here is the PSIM result that is done again by injection of a sinusoidal perturbation. And the dots are for PSIM that were done manually by us. And of course, it takes a long time in the two cases. But as you can see, the agreement is really very good. Also, we did a comparison between the average model and the full circuit model, or run, or transient run. In the average model, I don't have much time to go over all the details. We'll come to some of it later on. What we do is we replace the inductor and the switching by a continuous circuit, and we actually generate the average current on the inductor, and then we have dependent sources for the say output that are sampling the inductor current and feeding it to the output. So when we compare the small signal analysis done by PSIM, this will be the red, this will be the red one. This will be PSIM, and as it says here, and the black one is the analysis according to the average model done by PSPICE. You'll see that, of course, there's the two cases show practically the same response up to very high frequencies, in which case both analyses are incorrect because of course there is an error in the PSIM because the signal is very small and it's very difficult to get the information. Also, the switching frequency is in this case 100 kilohertz, and therefore of course the small signal injection around this frequency does not actually reproduce a nice sinusoidal waveform at the output. So PSPICE is incapable of doing the analysis. The black one is also incorrect because you cannot talk about small signal around the sampling or the switching frequency of 100 kilohertz. Both are actually limited to somewhere like here. So the agreement is actually pretty good. Now, the Simplorer implementation looks a little bit different. We recognize here the switch. This will be the error amplifier, and the output will be here. And as I've said, you can see on the same window both the circuit and the results. And here are the typical results of the different points. And of course, they are very similar to what we have seen earlier. except that, again, we are using here a generic rather than the actual transistor. The PLECS, which is a toolkit for MATLAB or Simulink, is generating waveforms which are very similar to what we have seen in PSIM. We see a little bit more details, and the reason is that we see phenomena which are around the transition, while in PSIM we don't see them at all. And here there is this spike which is part of a snubber which is actually implemented in the model circuit that we have been running. So you'd expect this spike actually to show. So, summarizing what we have seen, we can say the following. We have actually examined the four packages: SPICE, PSIM, Simplorer, and PLECS. And our impression is actually shown here with marks of good, good enough, and poor. Okay, poor for 1 star and up to good 3 stars. Now for user friendliness, we see that PSIM and Simplorer get the higher scores because you don't have to deal with file management. You just go in, write or describe your system and run the simulation, and that's it. You don't have to learn much about the general filing system and the way that you describe profiles of simulation and things of this nature. In terms of convergence, PSIM is the best. And the reason is that it doesn't look at the transients at all. So it really basically doesn't suffer from the problem of trying to overcome the very fast changes in the signals. For learning ease, we give also PSIM the highest mark because it's a simple program in terms of using it. You just open the window and you can, in a couple of hours, actually do a simulation from scratch. As far as the time to run a simulation in the time domain, again, PSIM is has the highest mark. The reason for that is that, again, it does not involve the handling the transition. For physical models of transistors and other elements, PSPICE is of course the best because we have a very rich library with many components, and we can use just about from many vendors, give us the libraries, extensive libraries of transistor, diodes, and other elements, which amplifiers, etc. As for the help menu, again, we found that we believe that PSIM is easy and very friendly, although PSPICE has pretty good help too. We have found that the other two simulators are less useful in this respect. As for digital control, then of course PLECS is the best one because it is a tool within the Simulink, and you can run quickly and try some discrete algorithms implemented in Simulink or MATLAB, and this of course is very useful. As for graphics, and what we mean by that is manipulation of the results, doing some calculation of the outputs. PSPICE, actually here we should say PSPICE rather than SPICE because we are talking about cadence now. PSPICE, then the PSPICE is getting the best score. Okay, the time remaining I'd like to devote to some of the results of our studies at Ben-Gurion University related to simulation. Due to the shortage of time, I'll have to run through them pretty quickly. Later on, I'll show you a reference or a link to our web where you can find references to all of these studies. The first subject that I'm going to present is simulation of nonlinear elements. Now, and I'm talking here as an example about an inductor. Why would you like to simulate a nonlinear inductor? Well, there are many reasons for that. For one thing is that real inductor, physical inductor, are nonlinear, and they depend on the current, and consequently, things like the ripple will change as a function of the current flowing through the inductor. It might go into saturation, and this phenomena you can actually, or you would like to see by simulation. Another reason for doing simulation on linear inductors are that you'd like to exploit or use the effect of low linearity for actually realizing a control inductor, that is an inductor that you can change its value by a command or by a control signal. Some of the oscillators, relaxation oscillators, are based on non-linear effects of inductance. And of course, the class of magnetic amplifiers are also based on nonlinear inductors. So how do we simulate a nonlinear inductor? The way to do it, or the way we implemented it, is very simple. We start with a linear inductor, and we translate it by a dependent sources, which are a function. We have E1, which is a function of the voltage at the primary, and G1, which is a function of the current at the secondary. And one can show that the inductance that you see at the input terminal will be K times L, where K is this parameters, or this constant, or this coefficient of this E1 dependent voltage source. Now, making now K a function of current will make the reflected inductance a function of current. And here is an example how we implement a dependence which is actually exhibiting or showing the saturation effect by actually changing the permeability or coefficient of permeability of this inductance. As an example of an application, if we consider a relaxation oscillator and or converter, what we have here is basically a saturable element, feedback winding, and an output winding. And what really happens is that this element goes into saturation, and then, of course, it changes the feedback path, and therefore it'll come out of saturation, and by that it'll switch from one state to another. I'm not going into too much detail here, except to say that the way we do it is, again, to reflect a linear inductor through a non-linear dependent sources. In this case, we have two other windings. This is the feedback winding, and this is the output winding. And here is an example of the performance. On the left side, we see the simulation, and on the right side, we see the actual measurement. And as one can see, that we have a very good agreement. This is the input current, or the main winding current, and this will be the voltage at the gate of the transistor, JFA transistor. Another area that I'm scanning here is average model of PWM converters, and the extension we have in recent year is to include more and more elements in this model. What we basically do, we take a generic part of all PWM converted, which we call the switched inductor, which, as you can see, is present except for the orientation in buck boost or buck boost. And what we do, we call this switched inductor, we describe it as a 3-port element. And what we are trying to do is to represent it by a average model that will show the average signals at the input and outputs. The added feature that has been extended in the last few years is to add losses, and this is done, for example, the loss across the diode and the loss across the transistor, and this is done by actually adding additional voltage sources that are power dissipated or dissipating power to represent the power losses here. Okay, so without again going into the details, what we do, we take the switch part represented by a continuous part which has some dependent current sources. We look at the voltage source drops on the diode and the transistor for generating losses, which are put here as series voltage drops, and the result of a modified model like this is shown here. The triangles are actually a result of time domain cycle by cycle simulation, while the continuous line is the average simulation. And of course, in this case, even though there's quite a bit of losses in the circuit, you see that you get extremely good matching between the time domain and the average model. Now, the advantage of the average model is, of course, that it is running much, much faster, about could be up to 1,000 times faster, and that you can do AC analysis, which, of course, is difficult to do in the transient analysis. I'm going to finish this presentation with the last subject that I'll present here, which is envelope simulation, which has been developed in our group. And it enables to look at a system which is driven by a carrier and to look only at the low frequency response, which is embedded in the envelope, rather than at the high frequency response. Now, we need it in many cases in which we have a system, for example, an electronic ballast that is controlled by a actually frequency. We change the frequency, and by that we change actually the current through the lamp. In this case, we measure the output, and we are interested in the amplitude, compare it to the reference, and change the frequency. In the case of a ballast, it will be the frequency. And in order to examine a system like this, you need to be able to translate the excitation here of the changes in frequency into amplitude changes. Of course, this can be done analytically, but it turns out that it's a very lengthy task, and a simulation tool would be very useful to do it. Now, we can do it, of course, with full simulation, which will take us a very long time and is limited to transient only. And with the envelope simulation, we look only at the low frequency. And however, we can use it. It says only, but I should say that we have since then extended the method, and it says only, but in effect we can do also small signal simulation by envelope. Now, how do we do it? What we do, we take a look at the excitation in a general way. This is a general excitation signal. It is correct for AM, frequency modulation, and phase modulation, and represent it in a phasor way, where this is actually the carrier here, and this will be a complex coefficient. The real part of it will be the representation of the excitation. Now, assuming that the output will be also of the same form, what we do, and I'm not going to, again, go into detail due to the shortage of time, we just handle these components and actually ignore the carrier, which is common to all which is a multiplier of all the expressions. And since we have here two elements, one is real and one is imaginary, we are actually running two circuits, one representing the real part and one representing the imaginary part. So we start with a network like this, which has a general excitation, and we break it into two parts. One is the real part and one is the imaginary part, and then combining the real part and the imaginary part as the square root of the squares of each part. As an example, suppose we have a piezoelectric transformer, which is a resonant circuit basically, and a rectifier. What we will do next, we'll describe it as a equivalent circuit. This describes the piezoelectric amplifier transformer. This will be the output section. And now we split again the excitation into the two parts, the real and the imaginary parts. And what we get here as a result of the modulation, this will be the modulating signal. This will be the this is the modulating signal. This is the carrier plus modulation. Of course, we can't see the modulation because this is in a time scale that we don't see actually the carrier. We just see the envelope of it. And this will be the input, and this will be the output. And in this case, you see the output has a change in the envelope since it was passing through the reactive network. The black line is the result of envelope simulation, while the gray here is the cycle by cycle or full simulation, which of course is taking a very long time. A feature which I've already mentioned is to be able to look at the small signal response. This will be between the output and the frequency modulation. And what we see here is straight lines which we got from the envelope simulation method, and the dots were done cycle by cycle with the full circuit, and of course the agreement is very good. This actually brings me to the conclusion of this presentation. I'd like to mention that some of the studies that I've mentioned were supported by the Israel Science Foundation, and also that you can get references to especially the studies that I've mentioned done at Ben-Gurion University at this link, our website. And if you just search for any keyword that you wish, you can get a reference paper. And most of the papers are in PDF, so you can download them. Thank you very much for your attention. And if there are any questions, I'll be happy to answer. Okay. טוב. אז אני מודה לכולם שעברתם את העינוי הזה. לא משנה, אני אמחק את זה אחר כך.
יש לי שאלה.
כן, בבקשה.
לגבי הפלקס.
כן.
אפשר להוריד אותו חופשי?
אפשר להוריד, לכל התוכנות, כולם יש evaluation.
כמובן.
וגם פלקס.
הפלקס הזה, הוא קשור ל-Power System Block Set, ל-Simplorer Block Set, אתה מכיר אותו ששם יש...
לא, הוא הרבה יותר חזק ממנו. ההוא, כן, כן. ההוא, Power System Blocks של MATLAB, הוא...
חדש, זה כבר נקרא Simplorer.
כן, Simplorer, הוא חלש. הוא חלש. הוא כזה לעניים, הוא לא רציני. כשאתם מתחילים לעשות... טוב, אני ברשותכם רק דקה אחת, אני באמת... אני אפסיק.